Welcome, everybody, to this week's Community Zoom at the Green Bank Observatory. I'm stepping in for Tony Remijan today. Just a little bit on observatory news. Tony passed on a few things that he wanted me to share with the community. Or remind people we're in the middle of summer shutdown, so we won't be observing again until September. If you have questions on how this affects your projects or your projects in general, contact your project friends. The painting contractors are on site and they're prepping to start painting. Basically, I think they'll start doing that next week. Last week we had the RAU boot camp at Green Bank. All the RAUs of all NRAO came to the Green Bank site and got exposure to radio astronomy. So that included the ones in Charlottesville and in New Mexico. The proposal calls. In Friday's e-news, you'll see an announcement, the NRAO pre-announcement for the upcoming 26A proposal call, which will be at the end of July. And that's for observations that'll be carried out starting next February through the next summer shutdown. Also in the e-news, there is some information in terms of cost savings the observatory has decided to make in these times, and that includes suspending support for community programs and some student programs, publication support, unfortunately, and some workshop support, science travel. The observatory regrets having to take these decisions, and we will try to bring back these programs when the financial landscape becomes more favorable. So if you have questions about that, please ask and read the e-news article that's coming out on Friday. So I'm going to hand it over to Jay, who will be introducing our speaker.
Thanks very much, Dave. Our speaker today is our own Jacob Turner, a postdoc at the Green Bank Observatory, and he'll be speaking on an extreme scattering event towards pulsar B2310+42. Let me remind everyone that this presentation is being recorded for future viewing, and please submit questions that you may have using the Q&A box at the bottom of your screen, and we'll get to them at the end of the presentation. Take it away, Jacob.
Right. Share my screen and we'll get going. That should be visible, right?
Yes, we see it.
Looks good.
Cool. All right, cool. Yeah, so I'm going to talk to you for the next couple of minutes about this exciting finding that myself and one of my students in the Pulsar Science Collaboratory found over the previous year-ish or so of data in one of our pulsars we observed. So I'm going to sort of start off. I'm going to assume most of the people on this Zoom know what a pulsar is. Just briefly, it's the core of a previously very massive star that died to supernova, and it emits these beams of coherent radiation from its poles. And we can use the rhythmic and predictable arrival of these pulses from these beams at our telescopes to understand many things about the universe. It's very versatile as sort of a naturally occurring laboratory. I use the emission from these stars, these pulsars, to understand the structure and behavior of the ionized interstellar medium in our galaxy. So I'm going to briefly take you on a quick journey of this emission as it leaves the pulsar, travels through the ISM, and eventually reaches our telescopes at Earth, just to give you an idea of how we actually do the analyses we do. So when emission leaves a pulsar, it is coherent. And that's really important because that means the phase information in those photons is going to be retained. And this emission is multipath, so this pulsar emits in all directions. And so we model this propagation through space in all directions as sort of initially traveling through more or less a vacuum. And then at some point along the propagation path, it's going to interact with a thin screen of turbulent plasma, which may seem a bit counterintuitive to some of you that aren't in pulsar scintillation science, just because you would think that the ISM along the entire line of sight would contribute more or less equally to scattering. But I'll provide a little bit of evidence later that this is a pretty good model. But anyway, so we're going from a vacuum to a plasma, more or less. And so that means we're traveling through different refractive indices. And when a photon leaves one medium with a refractive index that's different from a subsequent medium with a different refractive index, those photons are going to undergo a shift in phase. You can also think of this as scattering at some diffractive angle. But because these photons are all incident on this screen at different angles because they're approaching the screen from different angles. They're going to be out of phase with each other as they leave this screen. And so we're going to end up with this wavefront where we have a bunch of out of phase photons. And when their signal is recombined at our telescopes, we get this diffraction pattern. We get this time and frequency evolving interference pattern. And we can observe the effects of this through what are called pulsar dynamic spectra. And these spectra show the change in the observed intensity of the pulsar emission over observing frequency and time. And the bright patches you see in this image here, which are known as scintills, represent regions of constructive interference. And it turns out that the characteristic width of these scintillation features in both frequency and time can tell us a lot about the structure and behavior and even evolution of the interstellar medium along a given line of sight. In this case, this is towards pulsar B2310+55, also known as J2310+5531. This is already a pretty useful tool for understanding the interstellar medium, but you can extract more from this data if you take a two-dimensional Fourier transform of these dynamic spectra. If you do this and you have scintills that are fully visible in frequency and time, and the scintillation structure is fully resolved, you'll end up with these parabolic features in what's called your secondary spectrum. And these so-called scintillation arcs are the evidence that I was mentioning before that the majority of scattering happens along a highly localized region along the propagation of these photons. If the contribution from various parts of the line of sight was more equally distributed, we'd end up with a pretty diffuse column of power instead of these fairly constrained parabolic features. And for the purpose of this talk, I want to focus your attention to the new Fourier domain y-axis. This is delay. So photons that are scattered at larger angles in the ISM will result in images on this secondary spectrum that are higher up this delay axis. So larger scattering angle, higher delay. That I think is pretty intuitive. But the actual way these arcs are constructed is a bit less intuitive. So if you imagine a pulsar moving down and to the right in this image, and we have multiple photons leaving this pulsar heading towards Earth. If you have a photon that's traveling along more or less the line of sight, and you have a photon that's scattered at some angle θ1 behind the pulsar by the scattering screen, the interference of these two photons will result in some image on our secondary spectrum at some position here. And if we have a similar phenomenon where we have a photon scattered at a smaller angle θ2, well, that photon's going to take less time to reach our telescopes, so it's going to have a smaller delay, and we're going to end up with a scattered image that's further down this delay axis. And I'm only showing the top half of the secondary spectrum here. So this is delay 0. This is positive delay. Below here would be negative delay. But if you repeat this process for a bunch of photons scattered in front of and behind the pulsar's motion transverse to our line of sight, over a large distribution of these angles, you'll end up with a parabolic structure. And so that's where these scintillation arcs come from. Now, I'm going to use all this information to discuss a finding from some work I've done with a student in the past couple of months on what are called extreme scattering events. Now, extreme scattering events have been known in the literature for a few decades at this point. They were first found towards AGN. And the general idea of what's going on along these lines of sight is we have some sort of Gaussian-ish plasma lens. And if you'll imagine, I don't know if you can see my mouse, but in this bottom part of the figure on the left here, you have along the x-axis, you have time more or less. So you have different lines of sight through this lens. At the sort of termination of these lenses, you will have a convergence of multiple rays reaching our telescopes. And depending on where you are along the line of sight towards this structure, you will have maybe one or more of these caustic features in your data. So you can think of this y-axis quantity as flux density or intensity. But so as your line of sight moves through these caustic features, you'll end up with these spikes, potentially one or more, depending on, again, where the light is focused relative to where it's reaching your telescopes. And once you transverse towards the center of the lens serves to diverge photons. And so you'll end up with a large drop in observed flux density or intensity. And assuming the lens is fairly symmetric, as you reach the termination of the other part of the lens, you'll end up with more caustic features. In the extreme scattering event terminology refers to photons being scattered by these lenses at much larger angles than you'd expect from a typical distribution of scattering angles from your typical scattering screen. So these are typically much further off the line of sight than the extent of your scattering screen in many cases. And the manifestation of this in our data, at least in flux density, is more or less what I described earlier, where we have some sort of baseline flux density towards an AGN. Then we have a caustic spike, a sharp dip in, this is I'm looking at the top feature right now in case you can't see my mouse, a large caustic spike, a sharp dip in observed flux density, and then another sharp caustic spike followed by more or less a return to this baseline trend. And you'll notice that there is a frequency-dependent behavior here. So there are other subfeatures that appear if we look at this exact same source and same line of sight at the same amount of time at a much higher observing frequency. In this case, instead of 2700 megahertz, we're looking at 8100 megahertz. And you can see that we still have these caustic features, but there's some additional features as well in our data. So depending on when you like what frequency you observe at, your view or your line of sight towards the structure may look entirely different as far as the ISM is concerned, because photons are affected by the ISM to different degrees depending on what observing frequency you are taking data with. So what does this actually look like in pulsar data? Well, so certainly you can look at this with flux density. That's the figure on the left here, where you can see this is towards a millisecond pulsar. That's one of the better timers for pulsar timing arrays. But as you can see, we have this this caustic spike followed by a sharp dip, followed by a caustic spike again. There are multiple fits to this. Some of the models are looking at a single caustic spike on each side. Some are looking at multiple caustic spikes. That's what the different fits are. But the structure is generally the same, and there's no reason to think it would be otherwise because it's the same observable quantity. But if we look at this through scintillation, we can see different behaviors, or at least that's the assumption. Maybe we'll see different behaviors. But then when you consider what scintillation bandwidth actually represents, so scintillation bandwidth is the characteristic width of the scintills I mentioned earlier in observing frequency. Turns out that quantity is inversely related to the actual degree of scattering present in your data. And so with that in mind, one can make a pretty reasonable assumption that the behavior you would see in flux density during an ESE would be pretty similar to the behavior you see in scintillation bandwidth during an ESE. When there's more scattering, scintillation bandwidth is smaller, which we also see during the center of an ESE, the flux density dips, and during the caustic parts of the ESE, you have more focused photons towards your line of sight. And so you'll have a spike in scintillation bandwidth. So looking at the bottom panel on the right here, you can sort of see that behavior. There's not enough temporal resolution to see the caustic features, but you can see there's a multiple, one order of magnitude dip in observed scintillation bandwidth towards this pulsar during an ESE, during an extreme scattering event. And you can also see it corresponds to a pretty sharp spike in observed dispersion measure, which is the integrated column density of free electrons along your line of sight. And so through scintillation, we can actually study ESEs in pretty high detail. And pulsars in general are really valuable for studying the smaller scale structure of the interstellar medium. And when I say smaller scale structure, I mean sub-parsec in scale, so astronomical unit to parsec in scale. So with all this sort of introduction out of the way, I want to briefly talk about how we actually found an ESE in data using data from this group called the Pulsar Science Collaboratory. So this is a group this is an outreach group that is primarily run by graduate students and postdocs and maybe some professors that gives high school students and undergraduates the opportunity to participate in genuine high-impact astronomy research. We use the 20-meter telescope at the Green Bank Observatory, and this is really useful because this is not a telescope you have to apply for time for. You use this program called Skynet to submit observations effectively whenever you want. And so because of this, we can observe basically whenever we want for as often as we want. So we can get really high cadence observations on this telescope that may not be possible, especially not consistently possible, with larger telescopes for which one would have to apply for time for. And so with this program, myself and my student Zach Zelensky, who led this project, he started in this group as an undergrad at Penn State, and now he's a first-year grad student, or just finished his first year of grad school at Texas Tech. We found what we believe to be an incredibly detailed extreme scattering event, temporally speaking. We are almost ready to submit this paper. We just have a few more tweaks to the draft, and so hopefully you'll see this on the archive in the next couple of weeks. So as for our data, so on the left here, we have scintillation bandwidth over time, and on the right we have the measured distance to the scattering screen as a function of time. And I'm highlighting in these boxes where we believe the extreme scattering events to manifest. So one thing right off the bat that may be noticeable to some of you is we go from the fairly random fluctuation of scintillation bandwidths to this very monotonic increase, this very obvious, sorry, not obvious, this very deterministic, excuse me, increase, followed by a very sharp dip, followed by another decrease. And we believe this is a resolution of the caustic features of the extreme scattering event. Certainly we've resolved what we believe to be the center of this lens through this sharp dip. But these caustic features we don't think are have been resolved in other scintillation-based literature, so that's exciting. And perhaps more evidence that this is due to an extreme scattering event is the sharp change in observed screen distance, so scattering screen distance that we measure over the course of when we believe this event takes place. So we don't have the best gauge of estimated screen distance to this pulsar before or after when we believe this event to occur. There's a fairly wide range of estimated distances, but during the same time frame that we see this interesting structure in our scintillation bandwidth, all of a sudden, all of our measured screen distances converge to a really highly constrained, relatively speaking, region in screen distance space. And then after this event terminates, or when we believe the event to terminate, the screen distance fluctuations go back to what they were before. So we believe that whatever is happening in this range of about 220 days, it has to come from a much more highly localized structure along the line of sight. And when you do some pretty basic geometry, you realize that whatever this is must have been from a feature that was around 15 or 16 astronomical units in scale. So really tiny, but enough to cause a pretty significant change in the time series of our data. A current unknown at this point is the actual electron density of the structure, and we are looking into that. But on top of this behavior, if we actually compare this extreme scattering event via model to if we just expected this trend to be explainable by just standard fluctuations in scintillation bandwidth via an MCMC, we are really highly favored towards an extreme scattering event plasma lens as a model for what's going on in our data phenomenologically. And this is evidenced by the base factor of these two models. So if we take the ratio of the Bayesian evidence of a plasma lens versus just random fluctuations, we get a base factor of around 200 compared to this relative to this other sort of baseline fluctuation model. And anything over 100 is considered pretty decisive. So this is more evidence that sort of to increase our confidence that what we're seeing in our data is quite real. And one other final piece of evidence is this interesting transient feature in our secondary spectra. So I include a couple of secondary spectra before, during, and after the event. And you'll notice that in the secondary spectra before the event and after the event, there's just a column of power. That's indicative of a fairly weakly resolved scintillation arc, nothing too special there. But during the event, we see this detached feature that's much higher up the delay axis than any other scattered images created in that secondary spectrum. And so what that means is whatever is causing this scattered image has to have been from some structure that caused photons to be scattered at a much larger angle than any other scattered images in our data. And again, when you do some geometry, you get that the scattering of this structure results in this angular broadening on the sky of around 0.14 milliarc seconds from a little over a kiloparsec away. And so that is pretty tiny, relatively speaking, as far as the entire sky goes. But as far as pulsar scintillation goes, that's moderately substantial, especially given how low the estimated scattering angles of other images in these secondary spectra are. So to give you an idea, the scattering angles from these photons is around 2 to 3 times larger than any scattering angle you get from something in the main body of these scintillation arcs. So all this together, all this evidence together leads us to believe that we have found an extreme scattering event toward the pulsar B2310+42. And this sort of begs the question, because given how small this event is, or how small the structure is that caused this event, you'd expect there to be many of these such ESE causing structures in the galaxy. And we have evidence for a handful of them in our data, but it sort of begs the question, why do we see so few? Why are these events so few and far between in our data? So that's sort of an open question that I'm sure many other people in the field have been thinking about for quite a while. But the more we find of these, the more we wonder why we don't find even more of them. So I guess with that, I will leave up my conclusions, and I'd be happy to take questions. Thanks for your time.
Thanks very much, Jacob. Please submit questions in the Q&A box at the bottom of your screen, and we have several already. Is the gravitational lens scintillation due to the Milky Way or the galaxy acting as a lens?
So in this particular case, this is not so much due to gravitational effects. This is due to scattering off of the free electrons in the interstellar medium. I'm not sure if that's what you're necessarily asking, though.
Yeah, it sounds like it's a somewhat different question. But how about, given the duration of the event and knowing the distance yields a velocity? Do you have that number?
Oh, you're talking about the velocity of the interstellar medium at this point?
Yes. Yeah.
I didn't include that in the talk. I'm sorry. I'm sure that's in the paper. I can't think of it off the top of my head. Whatever it is, though, it is much less than the velocity of this pulsar. I can tell you that much. But as far as the exact number, I don't remember the exact number off the top of my head. I'm sorry about that. But it's something. It's something like an order of magnitude, or at least a factor of 5 to 10 smaller than the velocity of the pulsar.
Here's another question. A question that I have. It looks like the length of the event was a few hundred days.
Yeah, about 220 days per our estimates.
Yeah. And so is that too short to be picked up in the monitoring that's done for the pulsar the nanograv?
That's a good question. So nanograv typically observes sources once a month-ish. Maybe there are some that are bi-monthly. I'm not entirely sure, but we observe during the course of this event once every 1 to 2 weeks. So it's possible you'd be able to resolve parts of the event, but given how few points we have during the focus of the lens, the center of the lens, you have to be fairly lucky in order to catch the most obvious part of the ESE.
Mm-hmm.
So it's possible, but I'd say you have to have some luck on your side.
There was a question which the questionnaire then answered about the possibility of these being from a coronal mass ejection. But again, I think at the time scale of hundreds of days and a size scale of 15 AU, that rules out that as being what you're seeing.
I mean, so there's been some attempts to just approximate whether or not scintillation arcs themselves along lines of sight to certain pulsars could be from the heliospheres of neighboring stars. I think the issue that we run into is just the mean free path of photons in the ISM doesn't seem to lend itself to influence from neighboring stars as a possibility.
We have a question as to whether these could be from a black hole accretion event.
That's interesting. So the assumption we make with these ESEs is that they're from interactions with free electrons in the ISM. Certainly, gravitational effects will change the observed behavior in how photons propagate through space. And we know that dynamic spectra themselves, the scintillation structure within them changes over time if we have a pulsar, for example, in a tight orbit with a companion. I have to think more about whether or not some sort of gravitational event like you just asked about would cause the same structures we see here. But it's an interesting idea. But I have to think more about it before I give a definite answer, yes or no.
Yeah, actually, Jacob, I think the question is not a gravitational delay in the sense that we understand it, but rather an accretion disk scattering.
Oh, I understand.
Yeah.
I mean, I guess accretion disks do get hot enough that they have ionizing radiation. That's interesting. I suppose it's possible. I don't know what the ionizing fraction of those disks are, but that'd be interesting. I guess the question is, so I don't know off the top of my head what the accretion disk size of a stellar mass black hole would be off the top of my head. But if it's on the order of AU, that'd be interesting.
Okay, here's another question. When you compute the Bayes factor, is it legitimate to ignore all other pulsars you sampled that did not show a similar pattern to find this one that does?
Oh, interesting. So all we were doing with our Bayes factor analysis was just modeling the ESC scintillation bandwidth trend under the assumption that there was a Gaussian plasma lens versus just random fluctuations in scintillation bandwidth you'd expect from both uncertainties and inner data and just fluctuations in the interstellar medium. So there was no consideration of other pulsars. And if you're thinking in terms of the likelihood of an ESE occurring along various lines of sight, we didn't account for that. But as far as the likelihood of an ESE occurring in our data, that's something we didn't consider. And so I guess you would have to factor in the ESEs occurring along the line of sight to other pulsars to consider that. But we didn't do that in our paper thus far.
Yeah. So here's a question again that I'll paraphrase by saying, is it the pulsar moving or your lens moving?
Yes. Although in cases like this, the pulsar velocity does dominate the system.
Okay. And here's a question. What fraction of the flux during the event can be attributed to the transient structure at 0.14 milliarc second separation?
That's a good question. So unfortunately, we don't have. So one downside of the of observing with the 20-meter telescope at Green Bank is that we don't get flux calibration. We don't have a flux calibrator source that we can observe with. We only observe the source directly. So I can't speak to that directly for this source. But if we look at previous observations of ESCs and pulsars, we can see that there's like a 50% change, give or take, in observed flux density over the course of the event. So it'd be fairly substantial. Of course, it depends on the source. It depends on the ESC, but it seems like you could expect fluctuations in flux density that are on the order of 50 to 100%, depending on how extreme the extreme scattering event is. So that would be my guess for what's occurring in our data. But again, because the 20-meter does not allow for flux calibration, I don't have that information for this pulsar.
Yeah, that suggests that while doing nanograv work, if you see a sudden decrease in the flux of a pulsar, you may want to start a separate program to observe it more frequently to look for these scintillation events.
Definitely.
Yeah. Well, that ends the questions and our time. We thank you very much for joining us today. And remember that this presentation will be available for viewing on the GBO website in a day or two. Please join us 2 weeks from now on the 18th of June when Rogman Bordaloy of North Carolina State will describe a new high-latitude H1 cloud complex entrained in the northern Fermi bubble. We look forward to seeing you then. Thank you and goodbye.